let's start today's session with the homework from last time, which was the following, if it were to show up. Please and thank you. Please. Thank you. There we go. You were given an integer value x, and you were supposed to generate a value y, which is equal to x to the power of square root of x. And the simplification I gave you was that the square root of x is guaranteed to be a natural number, so an integer above or equal to 1. And for this task, there are two major steps. The first one is to generate the square root, find the square root, and the second is to exponentiate x to whatever that result is, with the raising x to the power being the easier part, because that's just repeated multiplication, in the easiest method at least. And we're going to try that first. So we are going to have some value a. We're just going to have a temporary one for now until we have the actual program. So let's say we have an int a that's maybe a 2. Actually, let's just focus on our actual code right now. 81 is our x, and square root of 81 is 9. So let's just use a 9. And now we have to perform a repeated multiplication. And we have to do that exactly 8 times. We have to multiply x by itself 8 times, or 9 times, because that's our value. And there's a very simple structure we can use that I demonstrated last time that lets us repeat a certain operation or a set of instructions a certain number of times. And that was the for loop. And we're going to do that now. We have a for loop. We have for to indicate that we're starting a for loop. Then we have the brackets, and then we had the 3 different blocks inside the brackets in here that were limiting how often the loop is going to run, and give us some indication in between how far we're in the loop. First, we have the block that is executed once before the loop starts. And we're going to use that to initialize a variable that counts how many times we've gone through the loop. And traditionally, this variable is called I, which has a couple of different reasons. You could use I as an index or an iteration, or just because you need the I for int, maybe just a couple of different reasons why you might call it I. Also math. Math likes to use the I as well. Anyway, we're gonna count down on this loop. We're gonna start at a, so we're gonna set in our first block a variable I to the value of a. Then comes the second block, which is the condition. How often do we repeat? Exactly the same as in a while loop. And we're gonna repeat as long as I is greater than 0. So if I or a is a 1, we want to have the loop run at least once. So we have to include 1 in the condition. But if a is 0, we don't want the loop to run at all. So I greater 0. And then the third block. This is the code that's gonna be executed after each completion of the code block for the loop, right before the condition is checked for the next iteration. And usually you would use this code block to change the variable that's counting how many steps you've done. In our case, we want to decrement the iterator. We want to decrement I to go down from the high value a to at some point 0. We're going to do that with the simple decrement operation. I personally prefer to write it beforehand, though technically in C#, as long as it's standing on its own, I minus minus and minus minus I are not only functionally identical, but they actually compile to the same code in the background, as long as they're standing completely on their own. If you combine it with other commands, there's a difference, but yeah, this is my preference. This is gonna now loop through exactly 9 times, or whatever a is going to be. And inside the loop, we want to multiply x to itself a couple of times. We need some way to store that value, and that's where y comes in, which is already declared above here. Since y is going to contain the end result anyway, we just use that as a temporary storage. So we fill it with a initial value here, y equals 1. So this might be a little pitfall you have if you just used repeated addition to mimic a multiply operation. You would use 0, because if you don't add anything, if you multiply by 0, you want the value to be 0. But here we mimic exponentiation, raising to the power. We repeat multiplication, and in this case, if we do nothing at all, if the loop never runs, we want the value to be 1. And more importantly, if the loop ever runs, we want this code that we're going to write, for now with a bracket, to always work, which is y times equals x. So I'm adding the brackets here just to make that a bit easier to see, but of course we can't skip this since this is already the only instruction we want. But I prefer to keep it in right now, just for you to make it easier to see. And this is now gonna multiply x to the current value of y. Keep in mind, this is just the short form for y equals y times x. Right, this is the same. Just the short form. And we can actually put this inside the loop as well, but I'm not going to do that now. That's shortcuts that are not relevant for now. Anyway, this is the raising to the power. That's the easy one. What about the square root? There is no built-in function for square root, and we never discussed how to do square root. So let's have a quick, hopefully quick look, and please go to the next page. Please go to the next page. There we go. Let's have a quick look at how you might be able to create the square root or find the square root of a number. First approach, let's say we had the case where and x equals 81. That was the code we had before. How do we find the square root of this? First option, we just try every single number. Just guess a number. 1, is it square root? Nope. Take a 2. 2 squared, so 4. That's also not 81. 3. That's a 9. Also not 81. And just try every single number until we at some point hit 9. And yeah, that's our number. So we know 9 is our square root. That's perfectly valid, and at least for our simple demo program, that's fine. That's a solution. It works. And sometimes that's all you need. But there are, of course, more efficient ways to do that. I used the word guess earlier. Of course, now we guessed by starting by 1 and counting up. That's one way to structure our guesses to make it more organized. There's a different way to organize it, and the principle here is used in many different algorithms. Like the same basic idea is used in a lot of places, so it's probably a good idea to remember the basic idea behind this. Let's first look at what do we definitely know about the square root of this number. I already told you it's gonna be a natural number. We know it's gonna be at least a 1. So at minimum, it's going to be a 1. And we can definitely say the square root will not be bigger than the number itself. That doesn't make any sense. if it was just a 1, then it could be the number itself, but usually it's going to be smaller. So let's say the maximum will be 81, the number itself. We know the number is somewhere between 1 and 81, including the 2, for now. So just what happened? What happened? There we are. So we could just guess a number, or like earlier, take one of these two numbers. Like we can take the minimum now, 1 squared, so 1, which is less than 81. So we know this minimum is not the number we look for, and we know this is too small. 81 squared is, I don't even know right now, but it's definitely bigger than 81. So this thing is also not the number, but this one is bigger than the target. We know the actual number, the actual square root, is somewhere in between these two. Let's take just the middle. And the middle, right between, let's take 40. Oh, actually, let's take 41. Like that. So 41 is 41 squared. I don't even know right now. Well, it is bigger than 81. What do we know now? We know this is not the square root, and we know this is bigger than the square root. So actually, we now know this is the new distribution. We know the square root is bigger than 1, smaller than 41. Let's try the middle again. Let's try 21. And 21 squared. Also no idea, but still bigger than 81. So we know this is again an upper limit for the square root. And we can try that again. We pick the middle. 11. 11 squared, no idea, bigger than 81 still. Actually, no, I know what that is. It's 121. We're now in territory where I can actually make these squares. It's still bigger than 81. So we know this is bigger. We have a new limit between these. Now let's pick the middle again. Let's pick 6. And 6 squared equals 36, which is less than 81. So for the first time, we now have a value that's less than our actual square root. So now it's between 6 and 11. And let's pick the middle between. Let's pick 8. And 8 squared. That's 64, which is still less than 81. So another limit here. And let's pick the next middle. By the way, for the middling, I always go divide by 2 and then round down. Difference of 3 divided by 2, 1.5. Then we get to 9. 9 squared, 81, which is equal to 81. We found the number. Let's see. If we take this somewhat simple approach, took us 1, 2, 3, 4, 5, 6 guesses. Well, maybe if we count these two, it was 8 guesses. So at most, 8 numbers we tested if they are our square root, compared to the 9 guesses we would have had if we tried every single number starting at 1. So this is definitely the faster method. And this, we check the halfway point and then can discard half of our potential candidates. This principle is used a lot. If you think about it. By checking just the number in the middle, we can always tell that either the lower half or the top half of potential square roots is gone. They're not it. Look at the number line, it's maybe more visible. 181. So we check in the middle, and then we discard this entire field. And then we check the mill again and discard this entire field. Then we check the mill again and discard this entire field. Like in 3 guesses, we've almost removed every single candidate. Like most of it. It's just exponentially less and less. And this halving, like always checking only half of the potential results, we can express this in a different way. Keep in mind, we're working with binary numbers. So, what would that be? 32, no, 16, yes. 42. That should be it. That should be 31, if I'm not making a mistake here. 81, not 31. 31 was different. This should be 81. And remember that we're talking about binary, so each position here is twice the value in the previous one. In decimal it's always 10 times, in binary it's always double. So discarding half of the result set could mean we start at this first bit, the most significant bit, and decide is this a 1 or is it a 0? If it's a 1, it's... like if we look at the number line again, we check... if we could just look at 1 to 81. Okay, this is not quite the fitting... let's not use these numbers. But if we look at the number line, all the potential numbers we can express with 7 bits. With these 7 bits are gonna be on this line. And this top bit decides, is it gonna be in this one or is it gonna be in this field? The top one, the bottom one. And this bit, we then divide these two in further. This is gonna decide if it's in this one or in this one. Like this bit doesn't tell us if we're in the top or bottom part, but in each of these top or bottom parts it can tell the next half, and then in there we have another one. Right, this goes down and down, down, further to the least significant bit, which just is a 1. But we can do the same strategy as before. We start by checking is it the top half or the bottom half by just looking at one number and seeing if it's bigger than our target or not. And then we can just decide, hey, is this bit here gonna be a 0 or is it gonna be a 1? It's a bit more formal than the strategy we just used. Not that you can't use that, right? To look at it more in decimal way, just pick any number and pick in the middle, in half, and check then. That's perfectly fine, doable. I just try to phrase it more in terms of what are our numbers gonna be like. Structured internally, and may take advantage of that. And then something else we should look at that's also relevant for here. How many bits does a square root have compared to the number itself? We know x is 81, which has 7 bits. How many bits does the square root have? It's very simple. The square root will have at most 4 bits. At most. How do I know that? Well, this has to do with... this is a principle that applies to every base system, but it's probably simplest to see in binary. So let's take a number with 3 digits, or 3 bits. This is the highest one we can represent. This is the lowest we can represent with 3 bits. Right? Everything a 1, the highest possible one, and only the first bit is a 1, everything else is 0. That's the lowest we can represent. If the first one was a 0, then we don't really need it anymore. This would be just 2 bits now. Right? So if we need 3 bits to write down the number, this is going to be the lowest and this is the highest one we can write. if I multiply this number by itself, the lowest one, well, multiplication, and specifically in binary, is just I'm adding the number to itself at the position where the 1 is placed. So I'm adding this number to itself where the 1 is put, and now we have these two bits that overlap. But this is going to be my new number. The old one had 3, the new one has 3 plus 3, but minus 1 because we have an overlap here. If I do the same here, well, we have a bit more overlap. We have it once here, and once here. So we also get this overlap here, so to speak. But because everything has ones now, we have to make additions, and that has some carries. So we have a 1 here, we have a 0 and a 1. That's those two are 0. Carry bit. So those are also carry bits, so actually 1 0 means 1 there, that means 1 there, that means 1 there. That, did I make a mistake? I feel I made a mistake, but I'm not too sure which one. Anyway. Let's clean it up. That's multiplying this number will give us 6 bits in total. The biggest one, the most biggest numbers we can represent with 3 bits. This one will give us only 5. 2 times 3, 3 bits times 2, 6, minus 1 because of the overlap. Here we also have the overlaps, but because we have to constantly carry over 1 to the front, we get some extra bits in the end. So we push out the minimum length through the carry bits to get to 2 times 3, which is 6 bits. And this holds true for every system. Like, we have n bits, then we have, depending on the value itself, either 2n minus 1 or 2n bits. In terms of how many bits do we need to represent the number if we multiply this by itself. Actually, this counts for multiplication in general, but let's simplify it to the just I'm squaring up. So we know this is an odd number, so this can only be a 2n minus 1 case, and that means n must be 4. So we have 8 minus 1, and that means our initial number will have 4 bits at most. Well, actually it will have 4 bits, but I mean, it's a 9, so the 8, that's 9. The thing is, we can make use of that. So this halfway point, before I used 1 and 81 with just the decimal, not the decimal, the base 10 versions. No decimals, and whatever. Now we don't make a guess between 1 and 81. We know exactly we will need 4 bits at most for our 7-bit number. So just try 4 bits. Try to set the first one to 1. Check if the result is bigger than our target. Then if it is bigger, then leave that at 0. Let's try the next one. Set this one to 1, multiply by itself, check if the end result is bigger than 81. If not, then leave the 1, try the next one. Is this now bigger if multiplied by itself than 81? If yes, then, well, this has to be a 0, and so on. So we just go through all the bits from the most significant to the least significant. Always set them to 1, then multiply the entire number by itself, see if it's bigger than our target, and if yes, we leave it at 0, And if it's not bigger, we just set it to 1. We leave it at 1. And we do that for every single bit from the most significant one to the least significant one. Here we know 81 has exactly 7 bits, but to make our life a bit easier, we're not adding some algorithm here to figure out how many bits our number needs. We're just gonna assume every case is 31 bits, because it's an integer, it can store 31 bits. And follow our logic with 31 bits. The square root can have at most 16 bits. 16 times 2 minus 1. So we have to check 16 different bits. And we have to now find a similar way to here, a way to count exactly up to 16, and every time set a value to 1, or set a bit inside a value to 1, multiply that value by itself, check if it's bigger or less than or equal to our target value, and depending on that, keep that as a 1 for our final result, for the A that we're generating, or set that to a 0. Actually, we're going to remove the A here because we're going to need that at top. Let's put it in here. So A, and we're going to start off with an A that's exactly 0, because initially we assume that no bit can be set, and we're going to try to find bits that we can safely set. Now we're going to make a for loop, and I'm starting off further to the right because I'm going to need more space. And first, we're gonna start with an, let's use I again, integer value that is exactly 1 shifted over by 15 times. This, again, is just a bit shift operation, so we start with a 32 bits. Everything is 0 except for the last digit, the last position. The last bit is a 1. That's the value 1. And we're now shifting that over by 15 times. So this is shifting over by 1. This is shifting over by 2. And so on. And we're shifting over by 15. So shifting over by 1 gives us a 1 with 1, 0. We have 2 bits. Shifting over by 2 gives us 3 bits. So shifting over by 15 gives us 16 bits. So this is now a number 1 followed by 15 zeros. That, and it's gonna move that out here. Actually, let's remove that entirely. We don't need that anymore. We don't need this space here. Like that. And we're going to repeat this as long as I is greater than 0. As long as there are any bits we're going to check. And every time we've done our check, we're going to shift over I by 1. So we're starting off with the 1 followed by 15 zeros, and in the next iteration we're going to check a 1 followed by 14 zeros, then a 1 followed by 13 zeros, and so on until at some point we're just having a 1, and then in the last instance we have a 0, at which point this condition will eject us from the loop. And let's open the bracket here. What we're going to do inside now is, first, I'm going to make a simple helper variable. I'm going to call it TMP, classic, for temp, or temporary. And this is going to be A. And there are 2 ways we can do this. I could say plus I. This would be fine. If we just add our value, we know that the only position in I, only one position in I will have its bits set to 1. Everything else will be 0. And we know that because we start at the top and slowly go towards the right, our A, which we will increase later, will only have its higher bits set, the same bits we are looking at with I, but the low ones will always be 0. So when we add the numbers, there will never any overlap between two ones in the two numbers. We will never have any carries. So this will effectively set the specific bit that I is also have, that is also set in I. That bit will also be set in A. We can however do that differently with this one. You also have seen this before. This is the OR operation, but a bitwise OR. And this will specifically set all the bits that are both set in, or that are set in either A or I. And this will not do any addition operations, which makes it on one hand clear that what we're trying to do here, perhaps the programmer, and technically, depending on the machine, this could be a bit more efficient because addition requires more electronics than an OR operation. Technically, but I don't think that really matters in modern systems unless there's some kind of optimization. I mean, I guess when we go into SIMD territory, it might be relevant, but I don't really have experience on that part. Anyway, I'm leaving it that with an OR, with the single OR, not the logical combination between two Boolean values, just a single OR that makes a bitwise combination. And now we're gonna check if TMP times TMP, we're creating this square, just multiply the number by itself. If that is bigger than our x, operator order here would give us first the multiplication, then the comparison. Let's make that sure. The brackets just so we are clear that we first want to multiply, then compare it. Though I'm pretty sure that the order would automatically be this. And if that is greater, we don't want the bit to be set. We know this value is too big now. Conveniently, we only used the temporary variable. We didn't change A directly. So to not set the value, we don't have to do anything right now. So we can leave this empty. However, if that value is not greater, if it is less than our value, or even if it's equal to, we want that bit to stay set. So we use an else. And here we're gonna set A to TMP. And we were running out of space, so I'm making some optimization. Since we're not using this case up here, we can now restructure our code a bit. Just go directly for if it is less than or equal to x, the exact opposite of the previous condition. In that case, we're setting A to TMP. Assign the value we have. And then we can also close the bracket here. And that part is done. Did I forget that? Did I remove that earlier, or did I completely forget that the whole time? Let's ignore that. Let's ignore that. Not think about it. I will complain about it to myself when I see the bot. But I'm not looking forward to that. Anyway, now we have the first part. This one here, square root of x. And this one, x to the power of square root of x. So technically, this code will not create the proper result. Logically, this is correct code. Like, the computer can execute this code and it will, for other values, actually generate the correct value. In this case, there's something else we have to consider. 81 to the power of 9 is a very, very big number. I think it's about 2 quadrillion. But we store it in an integer value. Int y. We're using int temp, int a. And here we multiply x, an integer, into y, another integer. Integers cannot store up to 2 quadrillion. They can store up to about a bit more than 2 billion. That's about 1 million times less. So what can we do about that? Well, simplest solution, we just switch this to a long. And done. Alternative would be that we actually check for that condition down here in the loop and maybe give out an arrow. That would be a bit further down the line when we talk about that. Arrow handling and different strategies for that. For now, to get the solution, we just have to switch it to long. Long would be big enough to store a quadrillion or 2 quadrillion, and we would get the proper result. That was, in a bit longer form, your homework. And also the jumping off point for today's topic. This entire thing here was only to mimic a simple square root. And this is just for exponentiation. Wouldn't it be nice if we had an operator for all of this? Instead of doing it this long way, having just one simple operator that can do square root and one simple operator that can do exponents? We can do that. And we can do that in 2 different ways. One is a very advanced version of what we're gonna do next, so that's gonna be a couple of lessons out. But the basis will be the simple version first, which is called methods. If you remember the simple CPU I introduced you first, what is code in reality? It's not neatly written out program, like, well, not neatly, but what I have shown you just a second ago. It's just a bunch of numbers or values inside a computer memory that the computer just decides to go through, step through one by one, and depending on what number it sees, it will do certain things. Maybe set some other numbers, change numbers, do fancy things. And we always had the simple case of I have one program running. But you may also remember that there was never a stopping point for the program to end. The entire memory was full of potential values for programs. And we only ever used maybe, what was it, 40, maybe 50 at some point? For the really complex stuff later on. Okay, really complex. So there is a lot of extra space in there. And usually you would fill that space with other programs. And because this other space is perfectly accessible to the computer at any point, just by changing the program counter, well, that means we can at any point while executing one program in memory, just switch the program counter to a different address and execute a different part of the program, or a different program altogether. In a small scale, we already did that through jumping conditions, which lets us do loops that repeat the same code over and over again without us writing it again and again. And of course, jumps that move forward just to skip certain parts of the code, like our if instruction now in C#. That lets us decide which code to run. And you might look at it like having different programs depending on your input values. What if we had a special part in the memory that contains a program that could do things like calculating a square root? Since we can, at least in the lower level, just use jump instruction, we could at any point just jump forward to that part in the memory, have it execute the code for calculating a square root, put it somewhere special in a certain memory address that we know, that we as a programmer can be certain about that it will contain the end result, the square root, and then we just jump back to wherever we came from originally and continue that code. But now we know that there's a memory address that contains the square root. And when we need another square root, well, we just jump forward again to that specific part of memory where the square root code is. We execute that code, the computer has no problem with that, and once that's done, it will just jump back to the place where it originally came from, which will now be a different part of our code, but that's not an issue. It's just jump instructions, it's just moving the program counter back and forth. And so this behavior also translates to higher level languages, which still retain this feature in a different form, because it's way too useful for stuff like this. I want a square root function. I want a method to calculate square roots without constantly writing the code for calculating square roots. This is part of the higher structure in C#. So far, we only looked at executable code on this scale. We had operations and instructions and code blocks. And code blocks was already the highest level we could go to, the biggest scale we got to. But in C#, there's bigger scales than that. And that involves methods, because technically all of this code is like one method, one part in our memory that's one group of instructions that belong together. Like all of this is one part of our memory. Memory section A, section A. So when the computer runs this code, it will run our main code. But then down here will be section B, which has other code. But because it's part of the same memory, we could, in theory, at some point go down here, execute this code, and then go back up here and continue down here. We restructure similar to we do with an if instruction, for example, an if block. We restructure the order in which the code is executed. We just do it in a way that's larger than our program, because this part down here is not directly part of our main program. But we can still treat it like that by jumping forward and jumping backward. And then maybe at some point down here, again, jumping forward to that point and jumping backwards to here, to include this specific placeholder code in our main code flow. And usually you do that because you want to generate a certain value or change a value, and sometimes you just want to execute certain actions that require interaction with the registers. Like, for example, in the made-up CPU, that was the I/O. You want to read a value from outside the computer, or maybe you want to send a value to outside the computer. So it's not that you take existing values in the memory and change them and store them again back into memory. You take values from outside, freshly, newly into the memory, or you put values from memory outside. So we have different scenarios that are all replicated in methods that can get values from you to do stuff with, but they can also give values to you for you to do things with. And you can write methods that get values and give values as well. And you have the option to have methods that don't give you any values and don't get any values from you. So we have data goes in, data out, data in and out, no data in or out. 4 different cases. And basically we always expect for most methods that the data that gets out is one value, but the data that gets in, that can be several values. So it mimics the behavior of most operations. If you think of an addition, two values go into the addition, one value gets out, the sum of the two values. The structure for methods. The simplified structure is we have first the type that goes out. Then we have a name. Just like variables, the computer needs to know what method we're talking about when we want to use methods. Because you can define several methods, of course, not only one. So just like variables, methods have names. And that's followed up by brackets. And in these brackets, you can now have any number of variable declarations. Let's use variable. And another that and closing bracket. And then you have another code block where you write your code. Or you leave it empty, you can do that too. And example, if we have something like int a equals 5, int b equals 2, and c equals a plus b. Right? If we try to recreate this addition operation, we can do that with a method that would return an integer value. So we first start with int. So this part. Then we're going to take care of the name. And we'll call this add. Then a bracket. And this operation uses two integer values. So we're going to add two declarations in here. First have an int a. Then we use a normal comma and have int b, and then we closing bracket. Now we can write some code in here that will perform the operation and give us our value back. This part up here. This is the method signature. Usually it will actually be simplified where we skip these names and you just have int add, int. It just boils it down to the essential. This is the add method. Where is it? This is the add method. It will get two integer values from you and it will give you one integer back. Like this is the signature, the simplified version. This is what the computer usually deals with. This is the full signature where you can actually read as a programmer, okay, what are we gonna get? How do we use these values inside and what's not. Let's try to write the full add method now. Again, we have the integer for the return value. What are we gonna create? What is this method gonna give us back when we call it? What are we gonna call this method? And what do we get? Well, what does the method get from us? And what it gets from us is one integer a Actually, let's lose a space in here as well. And B. And then we can add the brackets. And for now, let's just create a new integer C, which is gonna be A plus B, because addition is already operation. There's not really a need for this add up method, but keep it simple for now. As you can see, we can just use these two variables as if they were initialized already. We're gonna leave some code out here. Let's look on the other side. And let's call it x equals 5 and y equals 2. How do you call this method? I wanted to now have an int z, which is x plus y, and I wanted to do that with a method. Well, instead of writing down x, then the operator sign plus, and then y, I just use the name for the method, add, followed by brackets, which are always needed. And in those brackets, then I write down the values that are basically placed in here. If these were initializations. So first I'm gonna put down the value for a, which is the x value. I add a comma and then I add a y and close the bracket, and that's it. What happens now is that let's actually make the good old table. This is the code we start with, and we have the type, name, value, our good old table. So first we have an int x, which we start off with 5, and we have an int y, which starts off at 2. And now we're declaring an integer z. What do you prefer, z or z? I'm gonna use that for now, which doesn't have a value initially. And now comes this part. This is the name of a method. It's a word followed by something inside normal brackets. This is a method call, and method calls are a form of operation. Like there's a generic operation basically, which is calling a method, and this operation will then call the specific method that you decided to name down here and give it the values you decided to place onto it. So in our case, we have, similar to operators, an x and a y that need to be resolved first. So add x, y turns first into add 5, then 2, first step. And then we're gonna make the call. We're gonna jump in the background in memory to the other part in the computer memory where this code is written. So we were at some point in memory reading this code, and a completely different part of memory is this code. And we're just gonna decide, nope, jump to this part up here. And now execute this code, as if there was no interruption at all. And when we do that, we actually create a new table. This is a new scope. The old table doesn't exist anymore. When we're up here, this table isn't known. We're in a different part of the memory, which has its own unique table. And what happens here is we declare int a, and now it gets a value as well. we only written down int a the declaration, but when we call the method, it will implicitly add the assignment of this value as well. So int a is here, this part is the declaration, and then because we called the method with a value of 5 down here, it will also initialize it with a 5. And then we have the integer b declaration, which usually would not have anything, but because this is a method call, implicitly we have the assignment of the value to this variable as well. So now we start here in this method in the actual code and already have these two values filled in our table. X, Y, and Z do not exist. This is our table. We only know A and B. We don't know anything about this code down here. We know nothing. We have nothing in common with this. We're in a completely different part of memory. The only things we are provided are these two values, which we use to initialize A and B. Otherwise, this is entirely separate program, basically. Now we're going to execute our code, which is integer c gets declared, and then we are going to make the operation a plus b and initialize the value to 7. Okay, what now? What is the magic code that I didn't write down here? Well, we're going to have to jump back to this code, right? And as I said, this code up here is entirely different part of memory, has no idea about this code down here. Everything is in its own table. No values remain, and we're in a completely different part of memory. So how do we go back? This code knows where this code is written. This add method is somewhere known in the computer memory. It's already there, and we can just reference that. So this code down here has to know what this add method is. But this add method does not know what this code down here is. No idea. No reference to go back to. It does not know where to jump back to. Even better, we can call the code again, second time. And we can call it a third time. And so we have now 3 different calls to the add method. And each time we would go back to here to execute this code. And then we need to go back down here to execute our normal code. And then jump back up and back down, but this time to this second add. And then down here we jump back to this normal method and then go back to our normal code down here. But third call now, this time. How is that handled? That is some magic that happens in the background that you don't actually have to worry about. What happens is that secretly, basically this table secretly has another value inside that is even initialized and set before any of these. And that is return address. Well, it's not actually called return address, but it's one of a couple of different values that are preset, and it will contain some mystery value that is the exact address in memory that we just came from. So the computer memorizes, hey, I'm calling this add method, and once we call the add method, we declared int a and int b, sure, and filled them with values. We initialized them from our call, sure. But what you don't have to do, what the computer does implicitly for you in the background, is also fill out a third value, a third parameter or argument, the return address, which is also now known to this method, but you don't get to see it. You as the programmer, you don't have any clue what that is. You don't worry about that. You just know the logic is sound. I call the add here, goes back up, and it actually uses this return address, secretly fills it in here. And when you call the add down here, it uses this address for the return address, and so on. So while you don't know it, the computer knows the return address, and it can use that. There's a special keyword that you can use to tell this method that it should now jump back to wherever the return address is. And that is return. Return itself can be just a full instruction. It's like one instruction that just tells the computer, take whatever return address you've remembered and go there. Be it here, or here, or here, whatever I decided. However, it's also an operation that can take an argument. And that is the value we want to return. Because this method add was defined to return a value. Was defined as it will give us a value back after we've called it, because we want to store it somewhere. So when we return, we have to provide the value we want to return, which is just written right after the return. Okay, so at this point, we've created our C, and then we call return with a value. Well, it will resolve the C. Return C is the same as return 7. So return 7. So it will jump back to the address that it has memorized right here. And so let's add that again. I removed that for some reason. It was 5.2. And after resolving these two variables, and after the method returns, after the computer jumped to this code, executed it, and jumped back to return, it will now replace this entire call with the value that was returned, which was now a 7. And now we can make z equals 7 here. And the same actually here and here. Side effect of having its own table, we can call these A and B. That's perfectly fine. Right? This table down here has a variable called A and B. This one up here is an A and B. But because they are separate tables, we can reuse the name for a different variable. We can also put it in reverse. We can call this one B and this one A. Same mistake twice. This one is B, this one is A. B, A, B. Let's use Z this time. Like that. And that still works. Like this time. B, A. In this part of the code, or our memory, like our original code, the one we started with, B is 5 and A is 2. But in the method, we have a different A and a different B. Same name, even same type, but they are different memory addresses. They are different tables in a different part of memory. So they only look the same, but they are very different variables. And so it's no problem in having different values assigned. Here, A is 5 and B is 2. That's perfectly fine. Can do actually more. One way here already. Well, this doesn't make too much sense. We could say that this method doesn't return anything. Again, doesn't make much sense, at least right now, not for this code. But we could decide that we only want to add this, but not do anything with it. We don't want to use this C at all. Perfectly fine. That's a legitimate way to do it. In this case, we don't return anything. We just have the return statement to just tell us jump to the return address. But now there's this void up here, where we should have written down the type we return. And the thing is, C# doesn't let us keep that empty. We have to put something in here. We have to put something in there. If we don't want to return a value, we have to specifically tell it by writing it in here. This is a void. There is no data type. Just keep it empty. That's fine. We as a programmer decided that this is not going to return anything. Either we return something, or we write down void to indicate that there's nothing to return. We can also go a different route again. Let's say this stays as an int, but this add doesn't get any values. In this case, we can actually leave this part empty. We do have to remove or return something. Since A and B aren't filled, we could maybe use 5 plus 2 directly. And that also means this part down here has to stay empty. Just empty brackets. Let's move them up a bit. Since they're staying empty, you always have to add the brackets even if they're staying empty. Unlike with code blocks where you can skip the curly brackets, for a method call you have to leave the brackets in there. That's important. So the computer knows we're talking about a method. Because it can confuse it for something else we're gonna see next time. But we can still use the return value like that. And it would fill the value 7 in here. And again and again. Keep in mind, it doesn't know C. So if I were to write C in here, actually let's keep the Z, the 7. If I had an int C, this would stay unset, undefined. We would never get a value. We have a C up here in this method, but this is an entirely different part of the memory. Completely different code. No overlap with this one. So the table and this table, they stay separated. This C and this C look the same, aren't the same. Keep that in mind. That's basically methods. So now going back. I said going back. Jeez. Oh, that was too far, too far, too far, too far. Forward. We have to move forward. We can't get stuck in the past forever. Like that. Actually, can I just... I'm wondering if I can return everything here. Okay, can I do it here, this way? Nope, I can't. I can't undo. Too bad. Alright, then let's now rewrite this with a method. Yeah, that works. I think that's cleared up. So we definitely need the x and we need the y, right? But for the square root, why not write our own method? Let's just restructure the whole thing a bit. Actually, while we're here, let's skip these brackets since we don't need them for this loop. Move it up. This is the exponent. Just put it down here, like that, maybe. Let's put that just maybe here. Okay, we're gonna need a bit more space for everything. So that was to work, like that. So this was our first method. And let's call... Hello? Okay. Let's call this first one square root, which we're gonna shorten. and it's going to get a single integer value from us, and it will return the square root of it, so another integer. So we have first the return value, the integer, which it will return, then the name, which we're going to shorten. We'll usually see something like sqrt, square root, then a bracket, open. Then we declare the variable that we're going to need, only one this time. We're going to just reuse the same name we already have, x, and then we're closing the bracket and we're going to start a code block. We're going to add it down here, and something we need to do now is this a wasn't declared in here. We don't pass on a. We needed a for our program, but that was always going to be initialized with a 0. That's not our input x. So this this int a, we can just move it here. Yeah, I'm making everything a bit smaller than it should be. Okay, I'm just kind of pushing it in there. So we now have an a that's gonna slowly change by setting individual bits until we reach a value that, when squared, results in x. So that a is the square root. And then we have to return this. Return a. This is now our square root function. This down here, actually let's move it a bit more. Like that. Same story. No, well. As long as it works. Let's use a long this time, because we already knew that the variable can be a bit bigger, so let's keep it big. And so this method returns a long. Let's call it, for now let's call it exp or exponent. Actually, let's not call this one y, because we're going to use y there. We have an int x and an int y here. And this is for x to the power of y. So let's call it r for return. That was fine. This x has to go. This y is, r has to go. Y has to move for r. That. And then we have to return r. Okay, it's all a bit stuffy, but we can now tell the computer to set y to the exp of, and this is something nice we can do. We can combine methods in themselves. We can now in here use, oh wait, not there. We first have to use x to the power of sqrt, and then x again. Closing bracket, done. So we have this and this. And this is perfectly fine, because just normal operator procedure, like every operator has a precedence. This is inside the brackets. This is necessary for the exponentiation. So the x is resolved first for the first value, this one down here. And the square root of x is resolved second, with a method call to square root for the second argument that's going to end up in y down here. So this code will now start with x equals 81. It will declare y, and then it will call this exp function down here, which will receive our 81. But it will also receive the resolved value of the square root function, which will return the square root of x. And it will multiply that a couple times and store that in y. And because those are methods, we can now do the same. We can do other stuff with sqrt, example from 100, like that. We can still generate a new square root by just calling the same method with exactly the same code we had before, just at a different part in our code, maybe with different values, usually with different values. And that's the magic of methods. We have one piece of code that we are now able to repeatedly call and reuse in different scenarios with different values. And if you imagine that inside these methods, there are maybe if blocks that change behavior, we even have variable code in here. We can change a method, or we can write a method that does different things depending on what values we get in. Not just different mathematical operations, but switch between entirely different branches of code. And because method calls are just normal operations, we can call methods in other methods. So we can write a method of, I'm gonna sort this out to the side here. So long big M special method that will get an int x. And what this does is it will return, gonna write this out a bit shortened, exp of x sqrt x, like that. This method m will internally just call the method exp, which first resolves sqrt. So generating the square root, then we exponentiate, and that's gonna be returned for m. So doing it this way, I can still call the methods on their own. Actually, let's do it. They still exist. I can still call them directly if I want to, usually because I need only one or the other, but I could also just go y equals m. Oh, wait, not m, m of x. I can also do this. Have methods, call other methods, which require even other methods to be called first, because they are basically operations, just a bit more tedious to write. I don't have a fancy little symbol I can use, like a plus sign. I have to use the full name, even if it's a shortened form of the name, and brackets. But it is still fundamentally the same, at least as far as the programmer is concerned. Those are methods. Very simple, straightforward system, actually. If you visualize just what happens under the hood. You just have different parts in memory where your code is spread, and you have some parts of your code jump to a specific known part in your code that does one specific thing, usually something smaller, and you then have that method jump back to the exact same place you originally came from, and then continue your normal code. And then at some other point you jump again to the same special address in your memory that does this one special piece of code, and then it jumps back to the place you called it from. That's important. You always jump to this special known location in memory, but this part in memory then jumps back to the specific part that you originally came from. So everything, all parts in code go to this one thing, but that one thing always goes back to exactly where the call came from. And then you can have the chains, like one method calls another method. Or things where you call two other methods in one method. And maybe they call each other. You can also have methods that call themselves. Perfectly fine. And you can have also methods that then call the other methods, which then call themselves. So this kind of nonsense is not actually nonsense, it can happen. So they are very special, they are a bit unique. And this property of calling other methods, including oneself, has a special name. If a method can call itself or calls itself to use itself instead of another method, it's called recursion. Recursion and self is nothing special. It's just a name we give to the unique scenario where we have a method that's not calling another method, but itself. It's like, I'm too lazy to program, so I don't want to write a program down here that can generate the square root of a number. The method square root now will just call the method square root to generate the square root. And whatever that method gave me is what I'm going to return. That's a recursion. And of course, that's kind of dumb because you call square root, which itself just calls square root to generate the square root. And it does so by calling square root again to generate the square root, which it does by calling square root again to generate the square root, which it does by calling square root again to generate the square root. You see how this is a bit not working? Well, it can actually work. And there are actually legitimate uses for recursion where, surprisingly, this approach of I don't know how to solve this myself, but I have a method that can solve that, so I'm just going to use that, even if the method is me. Like, by using recursion, a difficult problem can suddenly become very easy, especially for you as a programmer, by just offloading some of the thought process to the method you're actually writing right now. Like pretending like this method already exists and works, but you're using it in itself. Which is going to be part of your homework, to figure that out. So I want you to create a new method. I promise this is not as difficult as it might seem to you at first. But you are supposed to write a program. No, not write a program, write a method. And this one we're going to use the name POW for, because this is actually the name that's used for an official method that basically does that. But it does so in a very different way, of course. The POW short for power, because exponentiation, what we used exp earlier, is usually called POW. That uses recursion let me write that out in a way that you can actually read it. Brackets calls itself to produce x to the power of y. So example. And x equals 9. And y equals 3. Ln z equals w x y z equal 27. That should be the end result. Wrong, that's my mistake. Sorry. Of course it shouldn't be 27. That was a test, I mean. That was a test. You paid attention. Very good. It was 9 times 3, not 9 to the power 3. What do you actually have? 89. I can calculate. 720. Is that correct? 729? See, plus... Oh yeah, plus 81. That matches. Okay. This should be the result. And instead of a loop, you're supposed to use recursion. And I promise you that is actually a very, very simple method. Just try to use methods, and one single method specifically. So the signature is going to be long because we're returning a long, that's our goal. And the method is called POW. The signature is int x, int y, and homework. Yeah, I think that's it. Have fun with the homework. I promise you, recursion is super useful and important to understand, and actually super easy. It's only complicated when you let it be complicated. Which is not a recursion of itself, right? No, that's fine. Anyway, thank you for joining in, and I'll see you on the next one.